the period of this grandfather clock, and because of that, it's going to either lose time or gain time. You'll see in a moment. Over 1 year, they're asking by how much. Right? So I will be keeping my headphones on, and I will just try to solve this on the whiteboard. But I'll have my headphones on, so if you have questions, you can stop me and interrupt me, and I can try to answer your questions. Okay? So to answer this question, you will need to know the expansion coefficient of brass, and I did look that up. So let me just this. So this is problem 23. We have brass. So the expansion coefficient for brass is 19 times 10 to minus 6. This is in the book. I just looked it up from the books. And we start at the reference temperature of 17 degrees Celsius, and we end up some final temperature of 28 degrees Celsius. Right. So because of this temperature change, the brass is going to expand, and our clock is going to have a different period than its own. So you also will need to recall the relationship between the length of a pendulum, a simple pendulum, and the period, and that relationship is given by 2 pi L over G. Right. So hopefully you recall this. Even if you can't, maybe you can drive it by dimensional analysis or something. But you can also, of course, look this up. All right, so originally we had this P naught equal to 2 pi times square root of L naught divided by G, our original length, and then this length changes, and we're going to have a different period, right? Obviously something like this, G, and we want to see by how much this changes. So let's take the ratios of these two. So P final divided by P naught is going to, so 2 pi is going to cancel, square roots of G's are going to cancel, and we're going to have square root of L final divided by L naught, L0. Okay? And this L final is of course simply our initial length plus the change in this length. Now, there's a reason why I'm writing it this way, because I want to make an approximation, but this is a general strategy that you try to express things in a few variables as possible, and try to get to the variables that you can actually express in terms of the things you already know. And so I can rewrite this as a square root of 1 plus delta L by L0. Now, as you see, this expansion coefficient is a small number, right? So for a few degrees of change, this is going to lead to a very small fractional change in length. So this delta L by L0 is a small number, right? So because of that, I can actually take this and expand this using the so-called binomial expansion, right? So this becomes 1 plus a half delta L by L0. Okay? And so here I used binomial expansion, and that binomial expansion is something like this. So 1 plus x to n is approximately 1 plus nx for small x, right? Where the absolute value of x is much smaller than 1. So this is something you've hopefully seen before, and this is something you're going to use again and again in this course, and probably you're going to use it again and again in other courses as well, right? So this is nothing mysterious. This is, as I said, called binomial expansion. It is just the first term in the Taylor expansion of this term. Expand this around x equals 0, then you're going to get the first term looks like n times x. The second is going to be n times n minus 1 by 2 x squared, and so on and so forth. It's just Taylor expansion of this function around the origin. But when we take this, the exponent here is just a half, so that the half comes to the front, and we get this approximation. Okay? And that delta L is something we know. It's related to this expansion coefficients. So we can write this as 1 plus a half alpha delta t by, yeah, this is just alpha delta t, I think, right? Yeah. So this delta L by L0 is just alpha times delta t. And now these are all numbers that we know. Alpha we can look up. Delta t is just 11 degrees. And we can just carry out this multiplication and get some number, right? So this is approximately this. It's almost 1, but it's a little bit slightly larger. So the final period after this expansion is slightly larger than this original period, right? And the percentage difference, the fractional difference, is just this number here. So by how much will this change over a year is just this number multiplied by the number of seconds in a year, right? So they're asking us for this delta t over a year. And so delta t over a year is going to be just 1 year times the fractional change. In 1 year, there is approximately 3.15 times 10 to the 7 seconds. So this is 3.15 times 10 to the 7 times this number here, a half, 19 times 10 to minus 6 times 11. Right? Number of seconds in a year times this a half times our alpha times delta t. Right? And when you multiply this, you get something like, I actually calculated this, 3.3 times 10 to the 3 seconds, which is about 55 minutes. Right? So over a year, this is going to gain approximately 1 hour. So is this just lagging behind, or is this going faster? No, I think it's going slower. So when so this is telling us the period is longer. So let's say if we were at 17 degrees Celsius, if the clock had showed, let's say this started at noon, 1 hour later, if we were at 17 degrees Celsius, the clock will show 1 p.m. But this, because the period is now a little bit larger, is going to show something less than 1 p.m. Right, slightly less than 1 p.m. But over 1 year, these small differences will add up to about an hour. Yeah. So, do you have any questions about this solution? Now, this is not very, very challenging. It is, I think, marked as challenging because it combines a number of different pieces of information, in particular something from Physics 105. So if you're